Um, so just make sure that everyone knows what's what in Canvas. So as a pro assignment, I'll be putting links to them here. Then if that big any changes like to the schedule or whatever, I would try to update that here. And then for each class meeting, there's a discussion item. So for example, for one for today's class, and there's the link to this WebEx if you want to attend online. And here are the notes. So these are the notes that actually I started covering last time. And then after class today, I'll make any updates and I'll post it here. This is the previous class. That has links to the recording from last time, also the math diary. So these discussion items will always be posted sometime before each class. So here's one for today's class that for now just has the notes that I'm about to cover them. So this is what it looks like before class. I think you saw the other one is what it looks like after class. So I'll update that sometime this afternoon. So you can go back and see the notes, see the recording for any class. Okay, and for assignments, all the Canvas quizzes are there already, and then homeworks. First couple are put out there, and I'll keep pulling them up and go. One thing is, this is actually not the case for last semester. For most homeworks, I think every homework except for the first one and the last one, I'm going to have a separate document hints. So for example, under homework 2, so here's the usual list of problems, but there's also a separate hints document. Not every problem has hints to go with it. That's obviously some are harder than others. But be sure to consult that before asking questions, because it might be answered there already. And that reminds me, I need to add a link to the main page for homework 2. So let's go ahead and do that. As assignments go, first homework's not due for a while because I'm going to finish covering section 3.1 today. That's what homework 1 is on. Usually, the general rule of thumb is that once I finish covering a section in class, then you have about a week after that point to finish the homework for those sections. Is there a question?
Oh, I don't want to interrupt you.
But
okay. So apparently you published the first 2 homeworks.
Yes.
So
do you want me to publish more homework?
Like you did last semester.
Yeah. I can do that. I mean, besides the stuff is there. There's always a possibility that I want to make changes. That's pretty unlikely, but yeah. I know why you're asking this question. Don't worry, I'll hook you up. Also keep in mind though, okay, since there are 9 homework assignments, but the lowest 2 get dropped. So that's don't avoid that. So looking at the semester pretty early. Okay, you play your card right. Okay, then I'll more say about the exams as we get closer and get those published when the time comes, but also sometime in advance. Okay. All right. Okay. Any other questions before we return to numerical linear algebra type things? Actually, I'm not sure how much time I'm taking today. But what was rather strange is, so here's the website from the last time I taught the class. So this is back, would have been 2 years ago. So yeah, I'm basically following the exact same schedule. So everything's just a day or 2 off. And for a second class last time, I had this MATLAB diary. And I thought, oh, I should go through that this time. And so I had it right here. I put it up. And I was like, this is stuff from the next section. Why did I cover it in this day? So I'm not sure what I was doing. So I might not end up doing that today, but certainly at a more appropriate point. Okay. Besides the notes I have to go through, I'll take a look at the problems that I've assigned for this section and see if there's any pointers I should make. All right. Now, so where we left off, so just a quick recap from last time, that this is a problem that we're solving. Solving system of linear equations, ax equals b, where a is assumed to be a square and invertible matrix. So therefore, it has a unique solution. And where we got to at the end of last time, after looking at some simpler cases, is for a general matrix satisfying those assumptions, I derived this algorithm. So this is Gaussian elimination that goes through the columns of the matrix A from first to last, and performs elementary row operations, or really just one kind of elementary row operation, subtracting a multiple of one row from another to get what's called the row echelon form of a matrix that is upper triangular. And I made the point at the end of last time that when you're performing a row operation, normally what you would do, you really want that upper triangular matrix, you would, if you're trying to eliminate entries below the diagonal in a certain column J, and you're looking at some row I, where I is greater than J, you're performing the row operation. So what I'm doing is, I'm coming up with my multiplier, I'm subtracting a multiplier times row J. So I'll make a note of that here. J times row J from row I. This row I has non-zero entries from column J, J plus 1, etc., up to the last column N. So normally what you would do is you would carry out this subtraction for columns J through N. But as I mentioned last time, I have J plus 1 written here because we know what Aij is supposed to be ultimately. It's supposed to be 0. So there's no need to actually perform the operation. We just need to update the rest of the row. But at least actually before this algorithm, the upper triangle of A will contain the row echelon form. Now, okay. So continuing from that point, so we're solving a system AX equals B. And what we've just done, this algorithm here, is performing row operations on the matrix A. But we have, whatever we do to one side of the equation, we must do to the other side. So what I'm going to do is I'm going to take the algorithm from last time, and I'll just make a copy of that. Oh. It starts a new page, so it's not broken up across pages. Okay. So I'm going to, so when we perform a row operation on A, we also have to do the same to B. Now, B is just a column vector, so really we're just modifying one element. We're taking the element in, so I'm going to add that right here. So BI has subtracted from it same multiplier times the jth element. So this is mirroring what we see here. Now, in a regular linear algebra class like Math 326, you work with what is called the augmented matrix. You take a matrix A and a column vector B, and you smash them together. And you have this one matrix that has n rows and n plus 1 columns, and you just perform a row operation on the whole thing. This is depicted in the text. So you might write it this way, where you have entries of A, a vertical bar of any entries of B, and you just operate on all of them. In numerical linear algebra, we don't really take that point of view. We actually keep A and B separate for reasons that will become clear next time when I talk about the LU decomposition. But for now, keep in mind that we have to work on both sides of the equation. So right here, at least we're doing what we need to do to solve the system. So this is the algorithm that's presented in the text in section 3.1 for Gaussian elimination. So it's exactly this right here. So what this does is the A and B, the upper triangle of A and the whole vector B are overwritten with the result of performing these row operations in Gaussian elimination. So what we've just seen here, this is Gaussian elimination, reducing A to row echelon form. Or upper triangular. So that this system, the original system, we saw by a process I described last time, back substitution, which you can apply to any upper triangular system. Okay. So at least now we have an approach for solving A equals B, and we're going to spend the next section that's starting up on Wednesday and for all of next week improving that process, taking into account more what you would do, what you have to do when the computer is performing arithmetic rather than you doing it yourself like on paper. Okay. Now, point I want to make is that it was Gaussian. It comes from a very famous mathematician, Carl Friedrich Gauss, who developed a whole lot of mathematics in his lifetime. Gaussian elimination is not one of them. He's not invented. It was, in fact, there's evidence of Gaussian elimination like thousands of years ago, long before he lived, long before his time. And unfortunately, I cannot recall. I actually seen a presentation about this years ago from like the history of the American linear algebra, and but I know it's discussed how his name got attached to it anyway. But the problems related to solving A equals B, like least squares problems, and he did a lot of work there too. So maybe that's something to do with that. But so I'll probably have more to say as discussion goes on about the strange things that happen when methods are named after people. And it's just we're finding that these all kinds of things that can be legitimately named after him when he gets this too. Okay. Are there any questions at this point before I talk about efficiency? No. I do want to make one point before I move on, though.
Very much.
Yeah.
From that algorithm, can you emphasize 4K?
What about this?
Yeah, can you emphasize on that one for me? Like from that one.
Oh, this line right here?
Yeah.
Okay. Oh, about starting at the J plus 1 over J, that issue, or?
The K. 4K, like that's in a loop.
Okay. I'm not sure what you're asking me to do.
Yeah, I want you to explain further on that.
Oh.
On that algorithm. Like.
Okay. You mean about y is J plus 1?
Yeah.
Okay.
Why it's better, like, so you would type that in.
Okay. So what happens is one thing I showed this last time when I was like playing around with the row operations in MATLAB, that as you go through this algorithm, carrying out these steps, by the time you get to this point, and you're wanting to form this row operation, this row has columns 1 through j minus 1. The entries are already 0, so don't even worry about those. Now, a more, I guess, controversial point is that before you perform this row operation, aij is non-zero, presumably, and that is the entry we want to eliminate. So why don't we do it? The reason why is each row operation that we're performing to eliminate entries in column J, I'm talking about this second loop here. I perform row operations on each one of these rows, from J plus 1 down to the bottom. And each of those row operations, those are independent of each other. Now, what happens with this row operation will affect operations from later columns. So what I do in eliminating entries in column J, the whole rest of the row changes. That's going to affect what happens when I move to column J plus 1, J plus 2, and so forth. But as long as I handle, but they're affected by which columns? Only J plus 1 to the end. So what I'm doing here is the bare minimum that will ensure that subsequent row operations are correct. So yeah, when you carry this out on a matrix, and what will happen is your matrix will still appear, like you can inspect it afterwards, it'll still be an appearance of a dense matrix, it won't be up triangular. And you think, well, what is this garbage? But what happens is, you think about what are you going to do with this once you're finished? You're going to use back substitution. What does back substitution involve? The upper triangle. It will never look at the lower triangle, so it doesn't matter what's there. And we're actually going to exploit that to a next section for greater effect. But yeah, it's just a matter of, it's really boils down to, what are you using this for? This reminds me, I think that the single, if I think about the difficulties that students have when they've learned the mathematics, they know the theory behind, like they know their linear algebra, they know their differential equations, but then it comes to time to code up algorithms like these. And the thing is, math is challenging, coding is challenging, but they're very different challenges. And someone who can be very well versed in mathematics can have a lot of difficulty with coding, because you have to think in terms of not just following steps in a certain order, because I mean, executing algorithms like that, you're kind of doing that anyway in mathematics. You're applying certain problem-solving techniques, you carry out steps in a certain order. But then you also have your data, and your data is always changing. And what students have difficulty with is keeping track of, well, this memory location has this value at a certain point, then it gets overwritten with something, and we have to take into account and blah blah blah. It's that sequencing of steps and how it affects the data that you have takes a lot of getting used to. All right. Any other questions about this part? I should mention, to add to that point, I think one of the most consequential classes that I took, because as an undergrad, I was a mathematics and science major, and one of the early classes I took, it was, I think it was called systems programming. We spent the first half of the semester on VAX assembly language. So basically very close to machine language. And so your statements are very bare bones, carrying out just one operation at a time, moving this data to this location, or perform some operation on it, maybe doing a comparison, something like that. All broken down to single steps. And then the second half of the semester, we learned C. And by then, I'd already spent a year working with another language that some of you may not even heard of, called Pascal. Pascal was known as a very good teaching language, but nobody puts Pascal under kind of their curriculum anymore. Like CSC 101 here is all about C++.
I think they changed it to Python. Really? Yeah, for like this year, like this semester.
Oh, it just did? Interesting. Okay. And I wouldn't consider either one of those languages a good language out of the gate. But they want to jump in quickly. Because both languages are not so good for learning programming fundamentals. But learning assembly language, that it forced me to become conscious about what's happening with my data as I operated on it, step by step. And that's when I realized that when I learned C is really actually closer to machine language than you might think. It's just as a higher level syntax, so it's easier to write code in. And then maybe understand why it's used for systems work. That's very efficient for that. Just as Fortran is still the best language for mathematics because it is the most efficient. I mean, it may not be very friendly to code in, but when you really got to get the job done well, people still use Fortran. So any experience that you can get that puts you in touch with what's happening at a machine language level makes you a much better programmer. Because when I know about people who don't have that experience, they have a lot more trouble. Okay. Well, nice to have some unscheduled pontificating in there. Helps me fill the time. Okay. Now, okay. This algorithm will fail if this diagonal entry AJJ is 0. Now, can anyone tell me how do we avoid a situation like that?
Can you repeat your question?
Okay, so this algorithm will break down if this AJJ diagonal entry happens to be 0. What can we do in terms of the whole process of working on system linear equations to prevent that kind of situation from happening? That's not being done here.
In the code or
No, just like,
in general?
yeah, like if you're working in, okay, so if you were carrying this process out, say, on paper, you have like a 5x5 matrix or something like that, because you're just a glutton for punishment. And you're going through row operations, and then you work on your first column, everything's fine. You go to your second column, and you find that the 2-2 entry is 0. So then you're like, oh, I can't continue. So what would be a way to actually, I can come up with a case like that in MATLAB. This is 22nd. Okay, so I'm going to and it's a somewhat random matrix. Okay, so I'm starting with this. I want to perform row operations on it to make it up a triangular. So what I would do is so I'll start in column 1. All right, so second row is equal to itself minus, so I'll take the entry I want to eliminate, 2, divided by the diagonal entry in that column, which is 1. So this is a multiplier that I would use times the first row. Okay, and that makes this entry 0, which is what I want.
Thank you.
And then I do that again in the third column, so my multiplier would be minus 1 divided by 1. And then I do that one more time, the fourth row. My multiplier would be 3 over 1. Okay. All right, so I'm finished with the first column. I move to the second column, and I can't continue because I have A22 being 0. So how would I get around that?
Row change?
Yes. So to continue, row 2 with row 3 or row 4. The best choice is actually row 4. I'm not going to do that now because I'll be getting ahead of myself. That's something for me to be next section. And then you'll also see how I was able to come up with an example on the fly that would create this situation. If you do anything. Okay, so right there, that's a major deficiency of the algorithm that I just shown you. But that's something that we will address at the appropriate time. Any questions about what happened here? Okay. Okay, so now we're going to get into trying to evaluate efficiency of an algorithm. Now, there are different ways of measuring performance. Now, of course, the criteria that numerical algorithms, yes.
I have a question about the example you just.
Oh, this.
Yeah, you said that the best choice is row 4. Why is that?
Okay. Okay. You want the multipliers, the Mij, to be as small as possible. And the reason why is it reduces the propagation of rounding error. And to have the multiplier smaller means the diagonal entry should be larger. So the idea is, and I'll talk about this more later, but when you look for a row to swap with, you look for a large entry in absolute value. And it's like that. So all algorithms, they need to satisfy, numerical algorithms need to satisfy criteria of being accurate, being efficient, and being robust. Right now we're going to focus on efficiency. Now, a relatively simple way to measure efficiency is how many arithmetic operations is your algorithm performing? So this is floating point arithmetic. So the informal term for floating point arithmetic operations is flops. So if we can quantify the number of flops that an algorithm is performing as a function of some measure of the size of a problem. Now, for solving a system of n linear equations and n unknowns, n is a good way to concisely describe the size of the problem. So we have to know, in terms of n, how many operations does Gaussian elimination require? I should mention that MATLAB used to have a command called flops. I loved having a command. I was very disappointed when they removed it. It would tell you how many flops, how many floating point arithmetic operations you have performed during your MATLAB session. So after spending a lot of time in MATLAB, for hours at a time, then I would type flops in the prompt and say, you performed like how many billion operations? Like, wow, I was really fucking today. It even had special cases for the number of flops you performed was 0 or 1. If it was 0, it would say no flops. If it was 1, it would actually spell out for you. It would say, written out in full, a single flop. They got rid of it because they changed how they perform like this lowest level operations. MATLAB is built on a software library called LAPACK that's written in Fortran that has several numerical linear algebra routines. And they felt, honestly correct, so I had to agree with their decision, it's still important enough, that having extra code in there to count the number of flops, that's overhead that reduces the efficiency of their routines. So they took it out. But one time, I was implementing a well-known algorithm, one for computing eigenvalues. I thought, well, I want to compare the performance of my algorithm against theirs, because MATLAB has a function called eigen that computes eigenvalues and eigenvectors. So I could run them side by side and get the flop counts for each. Of course, mine was more, but I then made some improvements to my algorithm and trimmed it down pretty well. So it was becoming competitive with theirs. But now I have no way of doing that. That's unfortunate. So what we're left doing is trying to come up with examining the steps of the algorithm like this one, and trying to count up how many operations are in each statement. So usually the way we discuss the efficiency or the algorithm complexity is using big O notation. Now we saw big O notation last semester. Just to refresh your memory, that what this means is the actual operation count is bounded by a constant times whatever the expression is in here. So it gives you an idea of order of magnitude. So we're going to see this semester algorithms that have complexity big O of n, or n squared, or n cubed. Actually, I think those will be the only choices we'll see. So it's pretty hard to get something that's cheaper than order n. N is the size of your input. And anything like order n to the fourth or more, that's too inefficient. Okay. Okay. So for the simple systems that I covered last time, how to solve a system of linear equations when the matrix is diagonal or upper or lower triangular. Well, if you're solving a diagonal system, it's only n operations if you're performing n divisions, and you're done. With back substitution, the matrix is upper triangular, so there's somewhat more work to do, and it turned out to be exactly n squared operations. But okay, and a for substitution, the same process, but we will be using for substitution in a special case where the diagonal entries of a matrix are assumed to be 1. That's actually called a unit lower triangular matrix. So in that case, there's n divisions you can remove. So in that case, the diagonal entry of 1 is n squared minus n. So that's the complexity for these simple cases. So you can expect that if you're trying to solve A is equal to B for a general squared verbal matrix A, that there's going to be more work involved because these cases don't require Gaussian elimination. So we have to figure out how bad that's going to be. Now, what I will show you is that it turns out to be big O of n cubed. So it's no surprise that since you're working with matrix and have 4 non-zero entries, that things of order of magnitude will work more. And to be a little more precise, 2/3 n cubed. Plus, and there's lower order terms here. Now, what we're most interested in is the power of n. Like, so what kind of function of n are we dealing with? You know, linear, quadratic, cubic. So generally, the most expensive algorithms, like for solving systems or computing eigenvalues, things like that, turn out to be n cubed. You generally don't see anything worse than that. But it's not the only thing to pay attention to. This constant in front of the leading term, so the 2/3 in this case, that could be important too. We're going to see some algorithms later on for certain special cases for analog of Gaussian elimination, where the constant is 1/3 n cubed. So the constant is this 1/3. So yeah, you're saving half the number of operations. That's significant. So the at least the constant of the leading error term can be worth knowing too, because if you can cut that down, that could be very helpful. Like for example, if what we'll see is if the matrix in question is symmetric. Sure, we could use Gaussian elimination anyway, but there's variations that are designed for symmetric matrices that cut this constant in half. Okay. I also want to mention, while focusing here on counting flops, there's more to the story of efficiency than just that. So for one thing, not all arithmetic operations, distance, subtraction, multiplication, division, not all of them take the same amount of work. Multiplication and division are far more expensive than addition and subtraction. And some descriptions of algorithm complexity will break the count down. They're not just going to say X number of floating flops. It could be so many additions and subtractions in one category, and multiplications and divisions in the other category. And the reason why is floating point numbers are stored in a certain number of binary bits. This is something I was covered last semester. So if you think of a single arithmetic operation where the operands are numbers stored in binary, and you p digits of precision. Just think about when you first learned how to add, subtract, multiply, and divide in elementary school. You're doing everything longhand. That's effectively addition and subtraction take order p operations working on all those digits. You learned it on decimal digits, but the same is true in binary. Because with addition and subtraction, you line up your digits and work on them. Whereas with multiplication and division, like multiplication, every digit interacts with every other digit. It's like a big old FOIL operation is what you learned. You just didn't think of it that way. So the amount of work involved is order p squared. So multiplication and division have a far greater cost. Anytime you can modify an algorithm, if you replace a multiplication or division with an addition or subtraction, even if the total number of flops stays the same, you still make your algorithm more efficient. So that's one thing to keep in mind. Also, you're not just doing arithmetic. Storage is important. If you can minimize how many variables you need, then that can be very helpful. Transpose of a matrix is an operation that actually you like to avoid. And just because you're making a copy of that matrix, you're moving entries around, matrices are stored in a certain way. Matrices are stored linearly in memory because memory is one-dimensional. So in Fortran, which therefore MATLAB too, matrices are stored one column at a time. You have all the entries in the first column laid out in memory, then the entries in the second column, and so forth. Other languages like C or C++ use the opposite convention. They're stored in what's called row major order. So all the entries in the first row and second row. So that can be aggravating. That not all languages treat two-dimensional arrays the same way. So if you're actually accessing all the entries in a column, in Fortran or MATLAB are stored contiguously, so we can access them efficiently. But then if you're instead going across a row, the entries are spaced apart, so accessing them actually takes more time. It's those little subtleties that those who really get into programming. And this, I mentioned that this is one of the things I like about numerical analysis, that people who work in it can focus either entirely in theory, they might hardly ever write code. And then there are those who are all about the code, who will not care about doing a convergence analysis. And then there are people in between, which is kind of where I fit. There's so much to take into account. There's so many things that can be done to make an algorithm perform more efficiently that can really make a big difference. And while the key criteria is minimizing the number of flops, memory usage is a big difference to make. Also, computer architectures are always changing. There's a lot more parallel computing going on now. Parallel processing is a lot more accessible than it used to be. So some algorithms that were developed decades ago might not have been thought of as very efficient back in that time, but once the opportunity for parallelism came along, they're back in vogue. So there's lots to think about when it comes to you choosing the best algorithm and implementing an algorithm as efficiently as possible. And we're not going to get terribly far with that in this class, but at least we can tiptoe in that direction.
So in other words, an algorithm may be working like maybe efficient in theory, like on the board, but implementation-wise, not necessarily. Depending on the language, software, and hardware you have.
So in fact, I have a story about that from one of my first publications. So I submitted a paper, got reviews back on it, and the reviewer, one of the reviewers said that I should, so I'm using MATLAB anyway, I should compare, I'm from PDE, so I should compare my algorithm to using MATLAB's ODE solvers. So I did, and I'm doing these comparisons. MATLAB has several ODE solvers, and it was going pretty well, but the comparisons were favorable to my method. But then I tried out one MATLAB ODE solver in particular. It was called ODE-15S. S is for stiff systems of ODEs. And that algorithm was killing it, and it was killing mine. It was so much faster. Like, oh God, game over. I'm not going to get this paper accepted. What am I going to do? And so I found a way to make my algorithm faster, where I found that it was possible for me to characterize my method as basically performing a matrix vector multiplication with each time step. Now, that actually would involve more flops doing it that way, which is why I didn't do it originally. But once I did do it that way, then instead of using mostly interpreted code in MATLAB, which is a lot slower, it's using compiled code for something so fundamental as a matrix vector multiplication. So even though it was output more flops, it was so much faster, and now it became competitive with the other method, and the paper got accepted. Well, I'm often doing performance comparisons with other algorithms, so MATLAB has a nice feature called run and time. You can run some MATLAB code and have it timed, and it'll break down like, okay, X amount of time was spent in this function or on this statement. It tells you where the time is really being taken, so now then you know where to focus your efforts, because you don't want to waste time trying to make some part of your code optimal if it only takes like 0.001% of the overall running time. But really, there's usually certain hotspots where most of the time is being taken, and I've often made great strides in at least making it as fast as it could be, and learning about what kind of things slow your code down. Here's an example: if statements. If you have a for loop, and you want to do things a certain way, like the same way most of the time, but maybe there's a couple exceptions. Like you go and you have a for loop with I going from 1 to n. And maybe if I equals 1, you do this, and I equals 2, you do this, and all over I, you do this other thing. So then you think, oh, I put an if statement in my for loop. No, do not do that. Instead, what you should do is handle those exceptional cases outside of the loop. The overhead of an if statement, what does if statement do? It performs a comparison, and then based on the result of the comparisons, can perform some branch instruction to jump to some other point in the code. So that kind of code for performing computations in a loop is harder to make optimal. So if you can remove and that overhead happens no matter how the if statement plays out. The only difference is where it branches to. So if you just get all that stuff out of the loop, just focus on the default case, then you will notice how much faster your code is. So there's a lot of things like that to keep in mind. Here's another. How many times in an algorithm we might be doing something like an exponential or a square root? That doesn't count as one flop. Think about how those are being carried out. Exponential, for instance. It would be doing something along the lines of a Taylor expansion. Well, that's good. So each exponential square root or sine or cosine is a lot of flops. Now, I mean, certainly those functions are fine-tuned to be as efficient as possible, but it's a lot more work than like a multiplication or division because it's performing several of them. So if you can avoid doing that, that could be a good thing. Unfortunately, my methods do that sort of thing. So still pretty fast though. Yeah. So yeah, I could easily spend a whole semester just talking about this, about optimization. Alrighty. Okay, yeah, well, so one of the most famous algorithms goes to the fast Fourier transform, BFFT. Now, if you look at the definition of what's called the discrete Fourier transform, you just take a formula for it and implement it in the most straightforward way. It's transforming a vector of n elements would take order n squared work. But some observations that were made a long time ago led to being able to break a n point FFT into 2 FFTs of size n over 2. So you're bisecting the problem, and then just a little bit of cleanup after that. And then so we're going to reduce to n log to base 2 of n. Now, logarithmic functions grow a lot more slowly than polynomial functions. So as n gets large, there's a huge difference between these two. So opportunities like that need to be taken advantage of. Okay, so how do we get the flops? Where does that 2/3 n cubed come from? So here's a general layout of the algorithm. And, okay. Actually, you're gonna have go back and forth between. Okay. So we have we're counting the number of iterations for each loop. So the outer loop runs n-1 times. The middle loop starts from from row j plus 1 down to n. So you're counting the number of iterations. It may be a variable. So n minus j. And then there's one floating point operation here as a division to compute the multiplier. And then you have this innermost loop that also runs n minus j times. And then in that innermost loop, we have this statement here that performs a multiplication and a subtraction. So there's two flops here. And then similarly, there's two flops right here. So that's where these come from. So now that we know how many iterations each loop is carrying out and how many flops are carried out in each statement that performs arithmetic, we can you start from the inside and work your way out. So for example, this innermost loop, n minus j iterations, 2 flops each, so it's 2 times n minus j flops in total. And then the rest of the middle loop, at the second level of nesting, will have a total of that count from the inner loop, and then you add 3 more until you have that. And then the entire middle loop, you take the count from here, from inside the loop, and you multiply that by n minus j. So now you have this many flops in the middle loop. But now what you have to do is you have to sum that up from j equals 1 to n minus 1 to account for the outermost loop. So right here we have an expression for the total number of flops. It's not a very convenient one, but it's at least a starting point. Any questions about how that expression was arrived at? I should point out, we couldn't just take this and multiply it by n minus 1, even though the loop runs n minus 1 times, because your loop variable here is j. So the number of operations in this middle loop, since it depends on j, we actually have to sum it up from j equals 1 to n minus 1. So now we need to get this expression in what's called closed form. Informally, I mean not involving any summations. It's a lot easier to evaluate than this. So we use this summation formula as well as the simpler one that I'm sure everybody knows. Yeah. There's something wrong here. Yeah. So sum of the first n integers, n number of 2, and then we have this statement for formula for sum of first n squares. So both will help us here. Okay. So then we just go ahead and carry out the algebra. So starting at this point, I distribute everything. And then, so now I have this expression with 5 terms, so I break this up into 5 summations. Anything that does not depend on j, you're allowed to pull out. So I go ahead and do that right here. So in cases where you're summing 1, then you're just taking the difference between the starting and ending indices. So that gives me this term right here, and this term right here. And then, in all other cases, you're summing up j or j squared. So in that case, I'm applying these formulas. here, here, and here. And just, so now all of the summations are evaluated. So this expression right here actually is in closed form. It's just not simplified. So once I simplify it as much as I can, here we see the leading term 2n cubed over 3. That actually comes from this part right here, and then some lower order terms. So yes.
Can you scroll up just a little bit?
Yeah.
So once you do simplify it to J, you can use those. But where did we get those?
Oh, these?
Yeah.
Oh, I didn't actually come up with them. I just pull out the air. So
So we wouldn't have so if we were given a problem like this, it would be given to us, but we could.
yeah, or these could be looked up. Yeah.
Okay.
Yeah. So actually, the formula for the similar sum of J cubed is actually, I think it's this expression squared.
Yeah.
Yeah. So yeah.
Okay.
Maybe some of you know the story behind how this was first established.
It has to do with calculus?
No.
It wasn't, no?
Okay. It's actually from. Okay. And maybe it's
Is it by
maybe it's urban legend. I don't know, but supposedly it was developed by Gauss as a child.
Oh yeah, I remember that story.
Okay.
He was 10 or something.
What?
He was 10. I
Something like
think.
that. Yeah. Yeah. So his teacher wanted to punish him by misbehaving by telling him to add up all the numbers from 1 to 100, thinking he would take forever. But what he realized is that if you write out the numbers from 1 to 100, and then below them write numbers backwards, so 100 to down to 1, then so you have like 1 to 100 in a row, and then 100 to 1 in a row, and then add each column, so the columns sum up to 101. So then you can just, and the thing is, adding all of those numbers up gives you twice the sum you're after. So you take that 101 times 100, so n times n plus 1, and then you divide by 2. So we discovered that by making an observation in terms of how the numbers were written. So I don't know how this one came about. Probably not as interesting. Yeah. But yeah, once you get to the point where the expressions in the summation are as simple as possible, and that's what these steps were about. Yeah, then you can just plug these in. Oh, you have no questions?
You will scroll down. So the last line. So you don't care. So you basically care for the highest power.
Yeah.
Just like with let's say with Taylor approximations, like the error.
Yeah. Because often it's certainly true in numerical algebra. You're working with matrices that or n can be quite large, and the larger n gets, the more negligible any other terms become. Yeah.
For Jn, oh, never mind. I thought it was squaring the whole thing. Never mind.
Okay. Okay. I think I've come to the end of the notes. Oh, yes, I have. Okay.
It's okay. I'm not done staring at it.
Okay. Now, but as I mentioned, this is a total number of arithmetic operations of any kind. It's just subtract, multiply, division. But what if I wanted to break this down by addition, subtractions versus multiplications and divisions? I would have to go back to where I started here. Like, for instance, this flop up here is a division. The two flops here are multiplication and subtraction, and then here too we have multiplication and subtraction. Now, since this right here is happening in a loop, okay, so if I do this breakdown here, so the number of additions and subtractions we have n minus j plus 1. Whereas multiplications and divisions, now that would be, n minus j plus 2. So it's safe to say that roughly half of flops are addition subtractions, probably more than half of multiplications and divisions. So, so you can say that, and this is what you would find if you were to work through the rest of this on one category at a time, that Gaussian elimination requires n cubed over 3 additions and subtractions plus 4 order terms, and then roughly n cubed over 3 multiplications. So in this case, it broke down evenly, but of course, it's not always going to happen. All right. So when you're solving a system of equations, it's Gaussian elimination that by far takes the most time. You're trying to order n cubed work just to get the matrix to upper triangular form, and then it's only order n squared work after that. What's going to happen starting on Wednesday is when we get to how computers actually proceed. It's based on Gaussian elimination, but there's some things that are done differently to take for sake of efficiency and for storage, and also how we handle rotor changes differently than what you're used to from the linear algebra class. Okay, so since we're finishing this section, 3.1, then you want to look at the quiz in Canvas on. So that's the first assignment that is due, and then start looking at the the first homework.
31st.
Yeah, so you have a good amount of time for it. Okay, so problems that I assigned, and some of these problems are going to be very frequent. So yeah, you could argue that some are too easy, but we're just tiptoeing in. Okay, 2, 3, 4, 5, 7, 8. But I think there's a reason why I did not put out a hints file for this assignment. Okay, so we're writing a short function to solve a diagonal system. Okay, MATLAB script to solve a triangular system like this. One thing to keep in mind is that yes, my problems come in several parts. There's more than one question asked, and the common loss of points comes from people ignoring some parts of the question. So, like something like this, for instance. So, please consider the whole question in terms of what you submit. Okay, modifying this for a general matrix. Yeah, also test your code. So because I reserve the right to run your code, and when you submit it in Canvas, I can easily download it and run it myself. And sometimes, right when I open the file, I can just tell, like, oh, they didn't test this at all because it's obvious that it would have crashed. So don't do that. Especially if I say the problem, test it. The best to help you make sure that you submit something that's correct, that you become aware of any mistakes. Okay, those are pretty short MATLAB problems. Okay, yeah. So you're working with a script from previous problems. Okay, previous ones from a 3x3 upper triangular system, but now an n by m one. So basically what you're doing is you're implementing this algorithm. So it's like translating this into MATLAB syntax. Then Okay, I did assign this one. 2, 4, 7, and 8. Number 7 was, okay, implementing this Gaussian elimination algorithm as it's written here. Okay, and I've accidentally given the answer to this away already. That does happen now and then, so, oh well, it's gonna be a quick one anyway. Okay, so, no real gotchas here, some of the problems in subsequent homeworks will be a pain. Sorry, not sorry. Okay, well, any questions about anything? All right, so we'll get into LED composition next time.